Assalamualaikum warahmatullahi wabarakatuh. I'm Adi. I present the theory of the experiment. Shear force, which is defined in structural analysis as the internal force in a beam that acts parallel to the cross-section as a result of external loading, is essential to the safety and design of structure elements. Shear stress is typically not evenly distributed throughout a beam cross-section, peaking at the natural axis and falling to zero at the top and the bottom surface of rectangular beams. The internal shear force V and bending moment M are directly related to the applied force Wx. Through differential relationship equation as mentioned, dv divided by dx equal to negative wx and dm divided dx equal to vx can add in locating clearer areas of the beam like the maximum bending moments at which shear force is zero. The distribution of shear force is affected by numerous beam types and support situations, such as a simply supported or cantilever beams, and each configuration necessitates a distinct analysis methodology. In reality, engineers have to take into account shear capacity, material characteristic, and safety consideration to make sure that the beam design avoid failure modes such wet buckling or diagonal cracking, especially in steel and reinforced concrete structure.
Selamat sejahtera kepada lecturer Madnan and NUU. I will present our result and calculation part for the experiment at shearing force. In experiment 1 and experiment 2, when we place different load on the position of the beam, we will obtain the experimental shear force which shown in the digital force display. After that, we determine the theoretical shear force by the calculation, and then we do the comparison to get the percentage error. This is the free body diagram for experiment 1. The theoretical shear force is equal with the weight multiplied with the distance between point A and width, and then divide with the total distance between point A and point B. The theoretical forces when 0.98 Newton is placed on point B is 0.573 Newton. And then we compare the results. The percentage error that's obtained is 4.71%. This is the free body diagram for experiment 2. The theoretical shear force at cut is equal to the algebraic sum of the force acting to the left or right of the cut. The theoretical shear force in finger 8.6 is negative 1.23. The percentage error with the experimental result is 2.44%. While in the figure 8.7, the theoretical shear force is 3.26 Newton. The percentage error is 4.29%. This is the free body diagram for figure 8.8. The theoretical shear force obtained through the calculation is 2.252 Newton. The percentage error obtained is 15.45%. Since the percentage error of experimental result in experiment 1 and 2 is lower than 20%, our experiment is successful and achieved to determine the shear force. We then record our results in the table as shown in the result and calculation parts.
Assalamualaikum warahmatullahi taala wabarakatuh. My name is Ahmad Zirwazi Bezukati. My matrix number is CD240 and 358. Okay, let's begin with experiment 1, where we examine how increasing the load affect the shear force in a beam. We use different methods ranging from 100 gram to 500 gram, and as expected, the shear force increased proportionally. For example, a 100 gram mass produced a shear force of 0.6 Newton, while 500 gram gave us 2.5 Newton. This result closely matched the theoretical value, with percentage error remaining below 5%. This strong correlation confirms what we know from beam theory that shear force increase linearly with applied load. It also showed that our experimental was fairly accurate and followed the principle of static equilibrium. Now, moving on to experiment 2, the focus was a bit different. Instead of changing the load, we keep it nearly constant but varied its position along the beam. This time, the results were less predictable. In figure 8.6, we record shear force of negative 1.2 Newton, while in figure 8.4 and 7, the shear force jumped to 3.4 Newton despite using the same total load. This clearly shows that load position has a significant impact on internal shear distribution. Although we observe some deviation from theoretical value, most of the error will still under 20%, which is really acceptable limit. This difference like came from an placement error, vibration, or alignment issue. Still, the overall trend align with theory and emphasize the need for precision in experiment setup.
All right. So now I'm gonna discuss about the discussion. I wanna present about the discussion of this experiment. And my name is Kiriwasan Alaki Mutu, and my matrix number is CD240354. So yeah, Basically, we have two questions. The first question is comment on the shape of the graph. What does it tell us about how shear force varies due to an increased load? As the equation we use accurately predict the behavior of the beam. Okay. Basically, the graph obtained from the experiment typically displays a piecewise linear trend, so which is characterized of a shear force distribution along a simply separate beam subjected to various loading conditions. So basically, in this experiment, we observed the shear force changes abruptly at the points of the applied loads and remains constant between them, so resulting in a horizontal line segment of the graph. So this behavior indicates the shear force between a segment of the beam does not vary unless an external force is applied at the point. And then, as the applied load increases, the magnitude of the shear force also increases proportionally. So this is consistent with the shear force equation derived from the principle of the static equilibrium, which is total force of Fy equals to 0, total moment force is 0. And then the equation used to calculate theoretical shear force accurately predicted the beam's behavior under static loading. So any minor discrepancies between the theoretical and experimental graph shapes may be attributed to experimental limitations, such as a slight misalignements in load positioning, and then also uneven load distribution or human error in data recording. So yeah, thank you.
Okay, so now let's talk about the second question, which is comment on how the results of the experiment compare with those calculated using the theoretical. So basically, when we compare experiment results with the theoretical calculation, what we observed is obviously the values obtained in the lab were generally in a good agreement with the predicted results. So there are some small differences we observed in some data points, which could be caused by several factors. I think so. What we see is potential sources of error include inaccuracies in load application, such as not placing the weight precisely at the intended position, friction in the beam supports, slight deformation in the beam material due to imperfections, and errors in measuring tools or data interpretation. So, despite this limitation, the consistency between theoretical and experimental results demonstrate the effectiveness of classical beam. And we successfully validated the theoretical principles and provided hands-on insights into how external loads influence internal shear forces within the structural elements.
To summarize the entire experiment of the shear force is that the concept of shear force in a beam under various loading conditions such as these multiple point loads and also the single point loads is successfully executed by using the help of universal testing machine. Moreover, the precision of theoretical prediction in structural mechanics could be evaluated by contrasting two different results. The first one is the experimentally recorded results, and the second one is the theoretically computed results. So the experimental results is recorded from digital force display, while the theoretically computed results are obtained from the force diagrams and the equilibrium equations. However, there are certain issues or problems that we face throughout the experiment. The major issue is that when the weight hook is positioned in a specific spot, it casually vibrates. Moreover, as the weight pieces were added one at a time, it caused them to not be aligned and the center of mass to deviate from the intended position. As a result, the weight hook location adjustment differs slightly and causing some deviation from the schematic experiment. To improve, we suggest multiple alternatives. The first one is integrating a sliding rail system and a location sensor displayed to the clamp weight hook at the exact spot, improving experiment accuracy. Moreover, this can guarantee that the weight behaves similarly to the schematic diagram. Additionally, to get an average result, the experiment is run over a range of time periods to make sure that it is consistent. And lastly, the beam could be polished to lessen the friction that is produced within it, which would change the ideal shear force under the conditions of the beam experiment. And that is all from us. Thank you for watching.